Okay, now let's move on to another example. Now we are going to simulate the probabilistic behavior, the behavior that have certain probability. And this is an example that the example that I mentioned last lecture. That is, you can sampling from the distribution by using this simulation types. Now we are going to sampling uh, and then simulate the coin tossing. It's very simple, right? Simulating coin tossing and estimate the probability of coin tossing. How to do that? When you toss a coin, you get either head or tail. If it's a pair coin, the chance is 0.5, right? You have probability of head equal 0.5, probability of tail equal 0.5. So if you're going to do Monte Carlo simulation of coin tossing, what you need to do is to repeat it a lot of time. If it's less than the probability of head, then you count it as head. So this is like you are tossing the coin for 1,000 times, and then you count how many times that head occur, and then calculate the mean out of that. Then you get the result, right? So I don't know why I have to send this. Okay, I need to share it. The second example, here it is. Okay, so I will just run it. Okay, let's take a look at this first. Just one run. One run would not do. You need at least more than one to estimate probability. Say you toss it 3 times and you want no 4 times, and then you want to calculate the probability of getting head. You get 0.25, 0.5. I'm quite lucky here, 0.75. Now let's move it to 10 times. Right, 10 times. You get 0.5, 0.5, 0.6, 0.3, 0.7. You can see the fluctuation there. Now, if it's 100 times, you get the value closer to 0.5. Right? If it's 1,000 times, you get the value almost at 0.5. So you can estimate, right? You can try it a lot of time and then estimate the probability of that really happening. You can see the convergence of the coin tossing. That is, when you increase the number of runs, the probability would converge to 0.5. Okay, when you increase the number of runs, the probability of getting head would converge to 0.5. That means for Monte Carlo simulation, in order to simulate something, you need to have a lot of iterations, and then you can estimate the underlying probability of the event through that. Okay. So important thing here is that you want to perform a lot of replication. You may perform a lot of replication. Replication meaning repeating doing that. And then from the repetition, you can divide it by the number of repetitions. You will see that later on in the stock example that I use. And you can use that to generate a random number. Right? How to do that? What we are doing there is to generate the U, right? U is from the uniform distribution from 0 to 1, and then if we were to say that this U come from Fx, come from the cumulative distribution, right? The value that we have here is the result of cumulative distribution. We can then inverse the function. Inverse the function, and then from U we'll get X, right? X is the inverse of U according to the above here. So if we inverse the cumulative distribution, we will get X out. And the inverse of the cumulative distribution is the quantile function, right, that we have in R. And we tried that last time, right? So we are going to try to do that now. We actually tried that in the lab, in simulating order size. So that is how it works here. Okay, so what does that mean? It means that from the uniform distribution, if we simulate generate a random uniform, you get distribution looks like this if you plot histogram. And if I use the inverse normal distribution function, I will get the normal distribution distributed at a random number of normal distribution. Is that true? We can try that out. Let me change it to this. Right, we can try this out. So if I generate you come from R uniform of say 5,000 point. I will get U looks like this from uniform distribution. Then if I plot the histogram, I will just use basic histogram here. I get the histogram that look like this one. Right? It's almost flat. So that indicates equal chance from 0 to 1. Now let's transform this U into something like normal distribution. How to do that? In order to do so, we need to have an inverse function. All right, let's take a look at this first. I'm looking at the normal distribution. I have this these are the functions related to normal distribution. We already have anorm. You can think you may say that why not just anorm? You can use that for sure. But what I'm trying to show you here is that you can act. What happens if you write in C? If you write in C, you need to have inverse normal distribution, right? The inverse of normal distribution that exists there in terms of equations. Let me. Um, all right, let me use this instead is codes. Right now, codes. Let me use this one instead. All right. In terms of the function here, we have the norm, p norm, q norm, and r norm. Right? Look at the detail. You see it will explain this. E norm give you the density, the probability at certain point of distribution function. P norm give you the distribution function. Q norm give you the quantized function. So we can use the Q norm and then convert. Or you can use quantize actually. Q norm, R norm generate number. And Q norm U. Right. This would get the quantile from the normal distribution of the U. What happened? We were to plot the histogram of that. And then, yeah, we got the normal distribution, mean equals 0, SD equal 1. And if you want to have different mean and SD, you can specify the Q norm, have mean equal 5, and SD equal 2, right? And here you get mean equal 5, SD equal 2. So you can inverse from the from the data from the distribution by using the inverse of the distribution. Then you can convert from the normal distribution, the simple normal distribution, into whatever distribution that you like. Right? You can convert it into Poisson distribution. You can convert it into the gamma distribution. If we need to just apply the inverse of the distribution or the quantile of the distribution, and then you can generate that distribution out. All right. So that is it. So you can apply the inverse distribution, and then you get the distribution that you want. Right. If you want exponential distribution, you can do the same thing, but you need to apply the inverse of the exponential distribution function, and you get this one, exponential distribution function. So for R, I need to use Q exponential for sure, but here is Q exp. There's no mean and SD. There's the rate value. Here you get the exponential distribution function of that. That means the value here, the value here can be used to represent the time between customer arrive at the store. Can be used to represent the time that the car passing through the street in front of you. Right? Can be used to represent the time that packet arrive between each packet arrival. Right? And then, or if you create a games, you can use this to trigger the time that customer come to the sim hospital, yeah, like that, from the distribution. Okay, that I for this lecture I have 4 examples to show you in terms of the usage of Monte Carlo distribution. That's the second example. Any question about the second one? Second example, simulating the distribution out of the data that you have. No, simulating distribution from uniform, then you can convert it into specific distribution. That means if you know that the data that you have obey certain distribution, like it is gamma, it is Poisson with this value, it is normal distribution with this value, you can simulate them without having to store the data because you can just store the parameters. All right. If you have the data and then you want to simulate from the data, I would suggest using quantile data. For example, if I use the number of infection occurring each day and represent it as Poisson, then want to simulate the next one, well, that's because it doesn't random, as you need different modeling for that. But for example, you have that data, you want to simulate a new point, you can use quantile to do that. Okay, if nothing else, let's move on. Next example is to let me check the time. Create the model of the stock market. We are going to create this is quite complicated example. Let's take a break. 5 minutes break. Right? And afterward, we will come back to take a look at a more complicated example. This one of the simulating stock price, and the next one, which is to simulate the portfolio. If you have portfolio, what is the chance that your portfolio will fail or the portfolio will be better? I will simulate the probability of that happen through simulation. Right, let's take a break, 5 minutes, and we'll come back after that.